Hello and welcome to lesson number 18, Derivatives Part 3. If you haven't seen the first part of the derivatives series, click this video right here. If you have seen that but you haven't seen the second part, click this video right here. So we are on part number 3, where we are going to be considering first off higher order derivatives, and then we'll be considering implicit functions and differentiating implicit functions, and then we'll be considering parametric functions and differentiating parametric functions. So let's go. Our first topic is higher order derivatives. So what we know as of yet right now currently is just what dy by dx is. Dy by dx is the rate of change of y relative to x based on a function, and in the common standard way we write that function as a function of x, as in you take the input as x, substitute the value of x that you're interested in, and then compute the gradient of that function. But note, dy by dx is in itself also another function. So we could take the derivative of this thing itself with respect to x. This is the idea of higher order derivatives. Let's consider, for example, y equals x to the power of 4 to explain the concept here. If we have the graph of y equals x to the power of 4, we know that dy by dx in this case is going to be, here relative to I, x to the power of 4 is going to be turned into 4x to the 4 minus 1 or 4x cubed. We know this from the previous video. So then the derivative dy by dx in this case is going to be 4x cubed. This is the first derivative. This is what we would call the first order derivative. But now notice, this is once again a function of x. So I can once again take the derivative d of dy by dx with respect to x, and in this case what we're going to have is the derivative of this thing with respect to x, which is going to be, here we have a constant of 4, here we have x to the power of 3, x to the power of 3's derivative is going to be 3 times x to the power of 3 minus 1 over 3x squared, and then that needs to multiply by 4 to get our final answer of 3 times 4 or 12x squared. This is what we would call the first order derivative. First order derivative. And then when you take the derivative of the first order derivative, that thing there would be then called the second order derivative. Now you can probably guess what the third thing is going to be. This is once again a function of x. So we can actually do it another time. We can take the derivative of dy by dx with respect to x. This right here is the third order derivative of the function y equals x to the power of 4. Writing it down, what we have here is 12 times x squared is going to give us 2 times x to the 2 minus 1 or 2x to the 1, or as simply 2x, and then we have to multiply by a constant of 12, which means we then have 24x. Once again we can take one more derivative. We can take once again derivative of the derivative of dy by dx with respect to x. Now you might notice that the notation that we are using here is getting extremely convoluted as we continue. So before we continue and write down this thing and the final answer, final derivative of the fourth order derivative, let's go back a bit and discuss the notation that we use to make this thing not look overly ridiculous. So here the notation we use is to consider what we are trying to express here, the derivative of dy by dx with respect to x. Here, if we just ignore the fact that these are not fractions, we could write this as dy by dx or something crazy like this. Again, I want to emphasize, this is not a fraction. This is not a fraction, and this is not a fraction. This is just the logic that we use to make our notation. So here you can see on top there are 2 d's, and over here you can see there are 2 dx's that we have to write. The notation that we use to write this thing is to write the d's as in d squared. So here there's 2 d's, so we do d squared, y by, there's 2 dx's we have to write, so we have dx squared. This is the notation we write. Once again, because of this notation, I want to once again emphasize, this is not a fraction. This is not a fraction, this thing is not a fraction, this is not a fraction. This is simply how we denote the higher order derivatives. So because we have to write d of dy by dx by dx, we write this instead as d squared y by dx squared. This is how we write the second order derivative. This also means that when we take the third order derivative, what we're doing is taking dy by dx and then doing that d by dx, and then we're doing that d by dx. So here once again, when we write this in the simplified notation that we have, we write this as d cubed y by dx cubed, because there's 3 d's before the y and then there's 3 dx's on the bottom. Once again, these are not fractions, this is just the notation we use. So anyway, continuing. Over here, what we had was 24x, which is the third order derivative, so I'm going to write third order derivative. And then we can take it once again. Again, you might be familiar with the notation by now. The pattern is going to be d to the 4y by dx to the 4th. Again, not fractions, this is just how we write it. This is going to be equal to, now here, to take the derivative of this thing, we have 24 times x to the power of 1. X to the power of 1 based on our formula is going to be 1 times x to the power of 1 minus 1, or 1 times x to the 0, or just 1. So therefore, the fourth derivative is going to be 24. So here, this is the fourth order derivative. Now then, we can still take the derivative here. Taking the derivative one more time, if we take the fifth derivative, d to the 5th y by dx to the 5th, this is going to be equal to, and over here what we have is 24 x to the power of 0, which means when we differentiate, we get 0 times 24 times x to the power of 0 minus 1, which is then just going to be 0. So then, the fifth order derivative here is 0, fifth order derivative. Now then, we can still go. If we take the sixth order derivative here, d 6th y by dx to the 6th, this is going to be the derivative of 0. 0 is 0 times x to the power of 0, and it's going to give us 0. So then, the next order derivative is 0. In fact, after this point, no matter how many derivatives we take, the derivative is still going to be 0. So this is the, not fifth, my bad, sixth order derivative. So here, for polynomial functions, as you keep taking derivatives, I'm going to write this as common formula, as you keep taking derivatives of any polynomial function, it is going to eventually become 0, and then every derivative after that is going to become 0. We have this kind of pattern for polynomial functions. However, certain sets of functions do not disappear like this. They instead continue indefinitely, perhaps in different forms, but they continue indefinitely. So here I'm going to write at the bottom, as a theorem for the polynomials, I'm going to write with a star, any polynomial eventually has an nth derivative d to the ny by dx to the n equal to 0. For any finite polynomial, if you keep differentiating, eventually you will end up with 0. However, certain functions, and in fact quite a majority of functions, do not have this behavior. One of the functions that does not have this behavior is e to the power of x. You might recall that dy by dx of y equals e to the power of x was equal to e to the power of x. So due to this fact, if we try to differentiate this one more time and then we say d squared y by dx squared, in this case, we're still going to get e to the power of x, because e to the power of x differentiated is still going to be e to the power of x. If we do it again, d cubed y by dx cubed of e to the power of x is still going to be e to the power of x. In fact, this continues indefinitely. E to the power of x is going to stay as e to the power of x forever. Some other functions which have this behavior are sine x and cosine of x. However, unlike e to the power of x, which is constantly e to the power of x, sine x and cosine of x have a certain changing nature when you take their derivatives. Recall, if y equals sine x, the derivative dy by dx is equal to the cosine of x. Now then, taking the next derivative d squared y by dx, what we have to do is take the derivative of cosine of x. The derivative of cosine of x from our previous video is negative sine of x. So here you can see, after 2 iterations, we have the negative value of our previous value that we had earlier. We had y equals sine of x, and the second derivative of this thing is negative sine of x. But it gets better. It gets better because we actually get sine of x back. If we do this 2 more times, the next derivative we are going to have is the derivative d cubed y by dx cubed, which is going to be the derivative of negative sine of x, which we can separate as a negative and the sine of x. So we have negative 1 times the sine of x. Negative 1 we can keep separately, and the derivative of sine of x is cosine of x. So then what we have here is the negative cosine of x. Taking one more derivative, the fourth derivative, d to the fourth y by dx to the fourth, considering this thing over here, we are going to have the derivative of negative cosine of x. So we can write that as negative 1 times the derivative of cosine of x, and the derivative of cosine of x is negative sine x. Multiplying these two, we just get sine x. So therefore, the fourth derivative of sine x is sine x. Here we have the symmetry re-emerging. You can see, after 4 repeated derivative takings, we get the same exact function. This also works for cosine of x. Over here you can see, if I take the fifth derivative, as in d fifth y by dx to the fifth, this is going to be the derivative of sine x, which is going to be cosine of x. We can see, for cosine of x, the first derivative of sine x is cosine of x, and then the fifth derivative of sine x is also cosine of x. So if instead of dy by dx equals cosine of x, here if we had y equals cosine of x, the fifth derivative would also be cosine of x. So we can represent this in the kind of circle. If we consider sine of x, and then we take its derivative, we get cosine of x. If we consider cosine of x and take its derivative, we get the negative sine of x. If we take negative sine of x and take its derivative, we get the negative cosine of x. And if we take negative cosine of x and take its derivative, we get sine of x. So it's cyclic. We are constantly repeating between sine of x, cosine of x, negative sine x, and negative cosine of x. Higher order derivatives like this are quite useful in that they can be used to predict the behavior of functions. However, that's going to be a video of its own. It's going to actually be the next video. So for now, we're not going to talk about that, and we're only going to talk about higher order derivatives. So in terms of higher order derivatives, the only things we have within our syllabus are the idea that when you take a polynomial, you can continuously differentiate it, and at some point you will get the zero function. However, anywhere in the middle you can still differentiate and get some value, and the meaning of this value is the rate of change of all the way down until we get the final original function. So here d cubed y by dx cubed is the idea of the rate of change of the second derivative with respect to x, and the second derivative is the idea of the rate of change of the first derivative with respect to x, and the idea of the first derivative is the zeroth function or the original function is rate of change with respect to x. That is all we have to talk about in terms of higher order derivatives. We'll just do a few examples of such and carry on to our next lesson. So let's take the example, let's say y equals x squared sine x and then minus 2x cosine of x. And let's take the derivative of this thing. We'll take the first derivative and say dy by dx is equal to. So now here we are going to be applying some of the rules that we found earlier in previous lessons, and well, that's going to be second nature to you as well. When you get to this kind of thing where you have to do this, it will be second nature to you. So here we have x squared times sine of x and minus 2x times the cosine of x. Here first thing we can do is split this thing into two separate functions and take the derivative separately. For the first function, what we have is x squared times sine x. Here we have a product of two functions, which means what we have to do is apply the product rule. X squared when differentiated becomes 2x, and sine x when differentiated becomes cosine of x. Recall that in the product rule, if we have f of x times g of x, its derivative is f of x times g dash of x plus f dash of x times g of x. So therefore what we have here, for the first bit at least, is the first function x squared times the second function derivative, which is cosine of x, plus, and then the first function's derivative, which is 2x, times the second function, which is sin x. So that's that. And then we have another function here. I'm going to put a minus over there, put this into a bracket, and then write the second function. For the second function, again we have a product of two things. We actually have a constant here which we can take out as a 2 here, so I'll write that as 2. Then we have x times cosine of x. Considering x times cosine of x, the first function is x, the second function is cosine of x. Writing these two down, x and cosine of x, again you don't have to do this is just me showing you how you would do it. For x, the derivative of x is 1, and for cosine of x is negative sine x. So then what we need is the first function times the second function derivative. So x times negative sine x, which is negative x sine x, plus the second function times the first function's derivative, which is 1, times cosine of x, or simply cosine of x. So then cleaning all of this up, what we have finally as our final answer is x squared cosine of x plus 2x sine x. And then over here minus 2 times minus x sine x is going to be another plus 2x sine x, and then minus 2 cos x is going to be minus 2 cosine of x. Now that we can actually group some of these, we'll actually do that. We can group this as x squared minus 2 times the cosine of x plus 4x times the sine of x. Now then we can still take higher derivatives here, because here we haven't diminished to 0. Taking the next order derivative, what we have is d squared y by dx squared. Now then, of course, here what we have to do is repeat the same pattern. Over here, taking this thing as our original function now and taking its derivative, what we have here once again is a sum of two functions. Here we have on the left this thing, and on the right this thing. This is a product of two functions, which means once again what we have to do here, take the first function, second function, first function's derivative, second function's derivative, and so on, and continue the pattern. So doing that, we'll do one more, and we're going to end it there. Then we're going to go to the next subject in our lesson. So here x squared minus 2 when differentiated, the minus 2 is a constant, so its derivative is 0, and x squared's derivative is 2x. So we simply have 2x plus 0, or just 2x. As for cosine of x, the derivative of cosine of x is the negative sine of x. So then what we need here is the first function times the second function's derivative, which is x squared minus 2 times the negative sine of x, plus the first function times the second function, first function's derivative times the second function, which is 2x times cosine of x. This is the first function's derivative right here, and then we have the second bit over here. So considering this thing, there's a constant 4 here which I could take out. Taking that out, we have x times sine of x. Considering x times sine of x is a product of two functions, which means what we have to do is apply the product rule. Applying the product rule here, x and sine x, x when differentiated becomes 1, and sine x when differentiated becomes cosine of x. So here what we have is the first function times the second function derivative, or x cos x, plus the first function's derivative times the second function, or 1 times sine x, so just sine x. Now then what we can do next is clean this up and make it nicer. So here cleaning that up, what we have is x squared times negative sine x, which is going to be equal to negative x squared sine x, and then minus 2 times negative sine x is going to be 2 sine x, so plus 2 sine x, and then plus 2x cosine of x. Then over here what we have is 4x cosine of x, 4x cosine of x, and then plus 4 sine x, so plus 4 sine x. Now we can group terms into one. Over here we have negative x squared over here, and then 2 sine x, and then another 4 sine x. So we can write this as negative x squared plus 6 sine x, so I can write as 6 minus x squared sine x. And then here we can see there's a 4x here cosine of x, and 2x here cosine of x, and 4x here cosine of x. Grouping those, we have 6x cosine of x. So you can see we can take higher order derivatives, we can keep doing this. In fact, since we have sines here and cosines here, this thing is going to be continuously having sines and cosines, and we can differentiate continuously. I'm not going to, of course, do that because I'll literally be here forever. So let's end it there. I would highly recommend that you yourself also write down some random functions and try taking their higher order derivatives to familiarize yourself with the concept of higher order derivatives. So we're going to discuss one more thing before we continue to the next topic, and that is notation. So I discussed how we do notation in the standard Leibniz method. This is how we do it. If we consider, let's say, first derivative, and then let's say second and third and so on. Let's say third, and we'll do fourth, and then we'll put dots after that. And then we have the three methods of notation. The Leibniz method, which I'm going to write in the first column here, and then we have the Lagrange method and the Newton method. So considering these, for Leibniz method, the first order derivative was written as dy by dx. In the Lagrange method, it was written as f prime of x. And in the Newton method, if we had some variable y and we had y equal to something of x, then we would represent the first derivative as y with a little dot over it. Now then, what I discussed initially for our purposes in writing these first things was that d squared y by dx squared is how we represent second order derivatives within the Leibniz method. Similarly, for third order derivatives, what we do is d cubed y by dx cubed, and fourth order derivatives is d to the fourth y by dx to the fourth. Similarly, now we're going to talk about what we do in the Lagrange method over here and what we do in the Newton method over here. In the Lagrange method, what we do for the second order derivative is to put 2 primes, so f prime prime of x. And then for the next one, what we do is to put 3 primes, so prime 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 of x. And then for the fourth one, the fourth order derivative, what we do is put 4 primes here. So fourth prime, f 4 primes of x. This is the fourth order derivative of f of x. And then in the Newton method, the corresponding thing that we do here is to add more dots on top. You might have guessed that already. For the second order derivative, what we do is add 2 dots on top. For the third order derivative, what we do is add 3 dots on top. And for the fourth order derivative, what we do is add 4 dots on top. Now you might notice here that little pattern here. What we're doing is stacking these dots in like a triangle way. This does not mean that fifth order is something like this, 3 dots here and 2 dots above here. It might be acceptable, but the standard way to do it is to put 2 dots like this, another 2 dots on top of that, another dot in the middle, and so on. So then this is how we represent the notation for higher order derivatives in our normal Leibniz method. This is how we represent it in the Lagrange method. And this is how we represent in the Newton method. So here again, if you see these kinds of notations anywhere, this is what they mean. Here we have the Leibniz method of notating higher order derivatives. Here we have the Lagrange method of denoting higher order derivatives. And here we have the Newton method of denoting higher order derivatives. Now we're pretty much done with higher order derivatives. As I said previously, do some on your own and try to see if you can familiarize yourself and better understand the concept of higher order derivatives. So then let's move on. The next thing we have to talk about is implicit functions and implicit differentiation. So implicit functions. Before we talk about implicit functions, we're going to first talk about what we define as regular functions. A regular function that we've dealt with so far, something like f of x, is equal to, let's say for example, x squared plus 2x minus 3. Over here we have a left side where we have just a function with a single input, and then on the right side we have some output where you substitute the value of x that you put as the input into each of these things and get the answer. So here this kind of function can be written in the form y equals x squared plus 2x minus 3, as in there's some other variable y that we can write when graphing, and we can say that y is equal to whatever the value of x squared plus 2x minus 3 is for whatever x is valid. This is all well and good for functions like this, where we have a single input turning into a single output, and we have a nice way to write the output on the left and the input on the right. However, for some functions we cannot do this. A common example for such a function is the expression x squared plus y squared equal to 1. This right here is the expression for a unit circle centered at 0, 0. This cannot easily be written as y equals something. You can try actually. If you do this, you can get that this is equal to y squared is equal to 1 minus x squared. But then when you try to write y equals, you need to do this odd plus or minus here, 1 minus x squared. We do not have exactly a function of the form y equals and then something on the right. Rather, the easiest way to write this function is to simply write it in this kind of format over here. This is what we call an implicit function. More generally, we tend to, instead of writing like this, write something is equal to 0. i.e. we say over here for the unit function, for example, unit circle for example, instead of writing x squared plus y squared equal to 1, we might instead write x squared plus y squared minus 1 equal to 0, and then say some other function which is our implicit function of x comma y is x squared plus y squared minus 1. We might tend to say something like this. So over here, this is an example of an implicit function. Over here, the reason it's not an explicit function like this thing up here is because we cannot easily write y equals and then something on the right. So then, if we have something like this, how do we differentiate it? I mean, here we cannot easily differentiate this thing, right? How do we differentiate it? Well, there's a nice method to do this. Here, let's consider an example function. Let's say f of x comma y is equal to, actually we'll take exactly this thing. We'll take x squared plus y squared minus 1, and we'll differentiate this with respect to x. So what I mean by that is the derivative of f of x comma y with respect to x. Over here, the derivative of the left side is the derivative of the right side. So this is the derivative of x squared plus y squared minus 1 dx. Since we have a sum of different functions here we have x squared, here we have y squared, and here we have minus 1, we can break this into the sum of each of their derivatives. So here what we can do is break this into dx squared by dx plus dy squared by dx minus, actually we'll put it as plus d negative 1 by dx. So here this is what we're expected to find. Now for the x thing, we can easily do this because we know how to differentiate with x's functions with respect to x. If we have the x function x squared here, we know that when we differentiate it with respect to x, we get 2x plus. And then I'm going to skip the middle part and go straight to this thing. We know how to differentiate negative 1 or the constant negative 1 with respect to x. This is going to give us 0. So we have plus 0, which I can actually erase completely because I don't really need it. So we can just keep that. Now then, how do we differentiate y squared with respect to x? Well, for this thing, what we're going to do is use the chain rule. We know that d of something, let's say d of a with respect to b, is equal to d of a with respect to c times d of c with respect to b. Here we are going to use this method to write this thing in a different format which we can figure out. So we're going to erase this thing down here. We're going to use the chain rule to write this thing in a different format. The format we're going to write is to write d of y squared by dx as d of y squared by dy times, and then we need to write dy by dx. This is the simple application of the chain rule. So then here we can now find this. We can find this because we know the derivative of y squared with respect to y. This is exactly the same as finding derivative of x squared with respect to x. It's just that we're now doing it with the variable y. So when we do this, the 2x carries down as 2x. Now over here, this thing we can evaluate. Y squared with respect to y is going to be 2y to the 1, or 2y to the 2 minus 1, which is 2y to the 1, which is just 2y, times dy by dx. And then this thing, as we remember earlier, became 0, so it's non-existent here. So therefore what we have is that the derivative of f of x comma y with respect to x is 2x plus 2y dy by dx. Now, you might be wondering, how are we going to use this in order to find dy by dx? Well, recall how we defined the unit circle is the values of f of x comma y when this thing was equal to 0. So therefore, we had another equal to 0 on the right here. Taking the derivative of this thing, the derivative of 0 is 0. So here, this is going to be equal to 0. Given that we can say 2x plus 2y times dy by dx must be equal to 0, meaning that 2y dy by dx is equal to negative 2x. Dividing out, we get that dy by dx is equal to negative 2x divided by 2y is equal to negative x divided by y. Therefore, this right here is our derivative of y relative to x. Now you'll notice here, we have a y in here, which means that this derivative here dy by dx is in itself also an implicit function. We do not easily have y and x separately in terms of y equals x format. Instead, dy by dx contains x as well as y. This, however, is not a problem. We can just substitute a certain value of y and x that we please and then use that in order to find the derivative dy by dx at a certain point. I'm just illustrating here the fact that you could have implicit derivatives as well. Then we could have second derivatives that are also implicit. Like we could take this thing here, we could apply the implicit differentiation once again and get a second order derivative which would likely also contain x and y in its formula. So here the concept that we need to get across here is that taking the derivatives implicitly is the same exact thing as taking the derivatives explicitly. Only thing is that we might run into circumstances where we cannot take the derivative immediately because we don't know how to do it. In this case, we couldn't find the derivative of y squared with respect to x because we didn't know the relationship of y and x directly. But we can take an indirect approach and use the chain rule here to turn y relative to y and then y relative to x, like this. While we're at it, I should mention another thing. Here what we've been doing is taking the derivative with respect to x. We could also take the derivative with respect to y. What I mean by this is we could instead take f of xy like this, f of xy as x squared plus y squared minus 1, and instead of taking the derivative with respect to x, we could take the derivative with respect to y. Doing that, we could take the derivative of f of x comma y instead of with respect to x, with respect to y. And now what we would have is the derivative is equal to the derivative of, here we have x squared with respect to y plus the derivative of y squared with respect to y plus the derivative of negative 1 with respect to y. And then we would have to do the similar thing over here. Here we have the derivative of x squared with respect to y. Since we don't immediately know the relationship of x and y, we can instead do, using the chain rule, d derivative of x squared with respect to x times the derivative of x with respect to y, dx by dy rather than dy by dx. And then here we have plus d of y squared with respect to y is 2y, and the derivative of negative 1 with respect to y is 0. And then over here what we would have is, this is equal to, here this thing is going to give us 2x times dx by dy plus 2y. Now then, since we had that this function f of xy is equal to 0, its derivative must also be equal to 0. This is also equal to 0, meaning that we have 2x dx by dy is equal to, taking this to the other side, we have negative 2y. Meaning finally we have dx by dy equal to negative y over x. Now you will notice again from earlier we know that dy by dx is 1 over dx by dy. We can actually see that reflected here by the fact that here we got dy by dx as negative x over y, and over here we got dx by dy as negative y over x. So we can see negative y over x, negative x over y, it is in fact 1 over the other thing. So here the only really important concept in implicit differentiation is the fact that you have to keep track of the variable you are differentiating with respect to, and then if you have any variables, any functions that you cannot differentiate with respect to that variable, you should use the chain rule in order to swap the variable you are differentiating with respect to and introduce a derivative into your function. So then let's do one more example and continue on to the next thing, which is parametric functions. Let's say g of xy being y squared plus 2xy minus x plus 3. Let's say something like this. Let's take the derivative of this function with respect to x and see what we get. So doing this, what we want to get is the derivative of g of xy with respect to x. On the right side what we have is the derivative of y squared with respect to x plus the derivative of 2xy with respect to x plus the derivative of negative x with respect to x plus the derivative of 3 with respect to x. Now then, doing each of these individually, y squared cannot be differentiated easily with respect to x because we don't know the relationship of y and x directly. Instead, what we can do here is use the chain rule and say that this part is equal to the derivative of y squared with respect to y times dy by dx. Similarly over here, for this thing, here we can actually take a 2 out here, which I'll do, and then we have the derivative of xy with respect to x, which we can do partly but we can't do the rest. Here this is a product of two functions, so if you take xy, d of xy with respect to x, we have a product of x and y, two functions x and y. So here what we have to do is multiply the first function by the second function's derivative, so dy by dx, and then add to that the first function derivative, which is d of x by dx times the second function, which is y. So here what we have as the derivative of xy is going to be x times the derivative of y by dx plus the derivative of x by dx times y. The derivative of x by dx is equal to 1, this is equal to 1, and then this thing is dy by dx. So here what we have here in brackets, I'm going to put a bracket here, is x times dy by dx, x times dy by dx plus 1 times y. So here plus y. And then removing the scratch work out, we'll go to the next term. The next term here is negative x. So here derivative of negative x with respect to x is going to be equal to negative 1. So we have plus negative 1 here, and then we have the derivative of 3 with respect to x, which is going to be 0, so plus 0. Now then, simplifying what we have here, we have the derivative of y squared with respect to y, which is 2y times dy by dx, so 2y dy by dx plus 2x dy by dx, so plus 2x dy by dx, and then 2 times y, so plus 2y, and then minus 1. This is the derivative expression of when we take what we get when we differentiate g of x comma y with respect to x. So then, since we would generally have this thing equal to 0 on the right side when we are finding the function, what we would get here is that derivative is also equal to 0, so here we have this thing also equal to 0, meaning what we really have is 2y times dy by dx plus 2x times dy by dx, which can be written as 2 times x plus y, so y like y plus x, dy by dx plus 2y, plus 2y minus 1 equal to 0. Rearranging this to find dy by dx, what we get is that this is equal to 2 y plus x dy by dx is equal to, and here taking the other things to the other side, we have 1 minus 2y. Now then, dividing both sides by 2 y plus x, we get that dy by dx, the derivative of y with respect to x, is equal to 1 minus 2y divided by 2y plus x. Once again, the derivative we get here, y relative to x, is going to be also an implicit function. Here we have y's and x's in here, which we cannot easily separate. So there. This is how we find implicit derivatives using implicit differentiation. The next thing we have to talk about is something called parametric functions. Parametric functions are somewhat similar to implicit functions, only they use a different concept. In a parametric function, instead of having a relationship of y with respect to x, we have something like y as some function f of some parameter, let's say t, and x as some other function also with a parameter t. So as in, y is given by some function of some value t, x is given by some function of some value t, and points on this thing are given by a combination of f of t and g of t. So any point represented by this thing will be of the form f of t, comma, g of t, and then for our syllabus, t is going to be an element of the real numbers. An example of this would be something like y equals 2x, comma. An example of this would be something like y equals 2t and x equals, let's say, t squared minus t plus 2. This is a parametric function of y and x. Now then, given this, how do we find the derivative of y with respect to x? Well, here once again we have to use the chain rule. We can take this function, we can differentiate it separately. We can take this function, we can differentiate separately, and then merge the two together to get dy by dx. Here's how we do it. For this simple example, we can do dy by dt. We can do this because we know the relationship of y and t. Over here, taking this thing, differentiating this function relative to t, we have 2 over here, because 2t is 2t to the 1, which is going to become 2 times 1 times t to the 1 minus 1, or 2 times 1 times t to the 0, as in just 2. Similarly, differentiating x with respect to t, as in dx by dt, we can do that as well, since we know the relationship of x relative to t. So then, doing this, using this thing, we can see that dx by dt is equal to, this term becomes 2t, negative t becomes negative 1, and plus 2 becomes 0. So then, dy by dt is 2, and dx by dt is 2t minus 1. Now then, what is dy by dx? Well, here, using the chain rule, we can see that dy by dx must be equal to dy by dt times dt by dx. Do we have dt by dx? No, but we have dx by dt, which is just as good. Do we have dy by dt? Yes, we do. So, alright. Now then, substituting these over here, for dy by dt, what we have is 2, and for dt by dx, what we need to put is 1 divided by dx by dt. So, what we need to put here is 1 divided by 2t minus 1. Simplifying this into a fraction, what we have is 2 over 2t minus 1. Therefore, this expression here is the expression for the derivative dy by dx. Over here you can see, usually what we would also do is to represent the derivative of dy by dx of a parametric function by its parameter. In this case we can see dy by dx is not in terms of y or x, but rather in terms of the parameter that we had, t. So here I want to go on a little bit of an anecdote, a little bit of a side note. Parametric functions such as this are quite useful sometimes. For example, the circle can be easily expressed in a parametric function in a different way. Over here, considering the parametric function of a circle, if we, instead of considering this thing like this, instead of considering like x and y and x squared plus y squared must be equal to 1, we could instead consider an angle theta, a radius of 1, and say that this point is going to be cosine theta, sine theta. So then, this right here is a parametric function for a circle. Instead of doing y squared plus x squared equal to 1, we could instead do x is equal to cosine of theta and y is equal to sine of theta for some parameter theta. And now here we can vary this theta anywhere between negative infinity and infinity along the real numbers and get different outputs of x, y. And then here once again you can see, if we differentiate this thing, here we can differentiate x with respect to theta. So here we can do dx by d theta, which is equal to the negative sine of theta. We could also do dy by d theta, which is going to be equal to the derivative of sine theta with respect to theta, which is going to be cosine of theta. And now we can find dy by dx as well. Even here, dy by dx is equal to dy by d theta times d theta by dx, and d theta by dx is 1 over dx by d theta. Therefore, dy by dx is equal to, this is cosine of theta, and this right here is 1 divided by the negative sine of theta. Cosine theta divided by sine of theta is cotangent of theta. So therefore, the derivative of this tangent to this function at this point xy is equal to negative cotangent of theta. So therefore, we can parametrically differentiate the circle in this format and get a similar answer to what we had earlier. Here what we have is equal to negative cotangent of theta. You can see here, if instead of substituting cotangent of theta and such, if instead I substituted here as cosine theta x and here as sine theta y, you can see we got the same exact answer as what we got when we did implicit differentiation on the circle. Over here we can see when we did implicit differentiation on the circle, we got an answer of negative x over y. Negative x over y is the same exact answer we got here, which we should expect. If we don't get the same answer, then it's a problem, because that means our mathematics is inconsistent. But you can see here, we get the same exact answer, except now we have it in a different form. An arguably nicer form, because here, instead of substituting two variables x and y, we just need to substitute one third parameter, as in theta. So that is it for this lesson today. It is a little bit shorter than the last two derivative parts. Both of them were like 1 hour and 20 minutes long. This one's shorter. However, we are not done with derivatives. The next lesson is going to be all about derivatives as well. It's going to be about analyzing the behavior of functions using derivatives. First order derivatives, second order derivatives. We might touch on third order derivatives, but those are not within our syllabus. So then, to summarize what we did in this lesson, first off, what we talked about was how we can take more derivatives. We can take the first order derivative as in dy by dx, but then if dy by dx is a function of x, as in like f prime of x, some other function of x, we can take the derivative of that function and write the derivative of dy by dx with respect to x like this. And then we could take the derivative of that and we could keep going. Within this, we talked about different notations to make it simpler. Instead of having d of something, of d of something, of d of something, of d of something, and so on, by dx, by dx, by dx, we could instead use this notation here. For the first derivative, dy by dx. For the second derivative, d squared y by dx squared. For the third derivative, d cubed y by dx cubed. And for the n derivative in general, d to the n y by dx to the n. Similarly, we discussed the other two ways of notating derivatives and how they carry down into higher order derivatives. For the Lagrange method, for the first derivative we have f prime of x, second derivative would be f prime prime of x or f double prime of x, and then the third derivative would be f triple prime of x, and in general the n derivative would be f prime 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 n number of primes over here of x. And then we talked about how we do Newton's method with this notation. For the first derivative, Newton's method has just y dot. For the second derivative, we have y double dot. For the third derivative, we have y triple dot. And for the nth derivative, what we have is a stack like this, stacked up all the way up, where we have n number of dots on top of the y. We also talked about the fact that when we denote this, it's standard to put pairs of two dots upward like this in a square pattern like this, until we get to the final dot, and either it's a single dot, in which case we put it in the middle, or it's two dots, in which case we put it to the sides like this. So that's that in terms of notation. And then we discuss some examples of how we do it. We discuss some special cases, like the fact that if we take e to the power of x dn of y by dx, in fact instead of doing this we'll put dn derivative of e to the power of x with respect to x is itself still going to be equal to e to the power of x. We also talked about the cycle of sine and cosine, saying that when you take sine of x and you take its derivative, you get cosine of x. When you take cosine of x and take its derivative, you get the negative sine of x. When you take the negative sine of x and take its derivative, you get the negative cosine of x. And when you take the negative cosine of x and take its derivative, you get the sine of x. This is a fourfold cycle. Every 4 times it iterates to get you the same exact result. And then once we finish that, we started talking about implicit functions and implicit differentiation. In short, an implicit function is a function of 2 or more variables where we cannot easily write the function as one variable equal to an expression containing only the other variable. So here we gave us an example, y squared plus 2xy minus x plus 3. Over here, it is not possible to easily put this function in terms of y equals and then some function of x. And then we talked about what you do when you have implicit differentiation. If you have a function of x somewhere in the middle, you can easily do this, you can differentiate this. However, if you have a function of y, let's say g of y, some function of y, and you have to differentiate with respect to x, you instead convert this into the differentiation of the function of y with respect to y times its derivative as y with respect to x. So like this, using the chain rule, we convert some differentiation that we don't know how to do into some differentiation that we know how to do, and the derivative of that function of y relative to x. And then finally we talked about parametric functions, how they are kind of similar to implicit functions but they have a different behavior. Instead of doing let's say y and x in one single expression, what we do instead is define y in terms of some function of a parameter, let's say t, and then we define x in terms of another function of the same parameter t, and then using this we plug in any t along the real numbers and get our point x comma y. And then during this we discussed how to take the derivative of this thing dy by dx. What we do first is take dy by dt as in f prime of t. Then what we do is we take dx by dt, where t is our parameter, so dx by dt as in g prime of t. And then we use the chain rule to write that dy by dx, the derivative of y with respect to x, is equal to dy by dt times dt by dx. And then these two functions here can be found from this expression over here. Dy by dt is f prime of t, and dt by dx is 1 over dx by dt as in 1 over g prime of x. So here this is going to be equal to f prime x divided by g prime x. And that is all for this lesson today. Thank you for watching and goodbye.